Welcome back to the second episode of the Let's Code series. In the previous episode, we started implementing a JSON serialization library using test-driven development. We started by listing our requirements and figuring out exactly what this JSON serialization system needed to do. We chose an interface and started implementing basic functionality like the ability to serialize built-in types, booleans, floats, integers, as well as strings. In this episode, it's time to get serious, as we are going to work on serializing custom classes. The tricky thing here is that the C++ language does not support reflection. We are not able to ask the compiler what the members of a certain class or struct are. For example, if a user were to pass an instance of an address class containing a street name and a house number, there's no way for our system to figure out that it needs to serialize first street name and then the house number. So we'll need to devise a way for the user to supply this information, tell us which members are in a certain class that it wants to serialize, without the user having to know anything about the JSON syntax, because we want to keep this system very generic and easy to use. Again, we will continue using test-driven development to slowly guide us to the answers, step by step, implementing one feature at a time, with one test at a time. Let's dive straight into it. For the next requirement, things get more interesting. We want to be able to deal with custom classes and structs. So now we get this thing, how are we going to serialize this address? I will again first write a test. And we'll use the address struct here. I guess we expect this to be an object, so we'll again use the braces. Street name is a name, so let's add some quotes there. I guess we expect something like this. Okay, here we see that this doesn't work because obviously we've never created a streaming operator that's able to actually handle address types. So let's change things up a bit. Instead of directly streaming the values, we'll introduce a new function for the serialization of these values. Just call it serialize value. And then we still need to do this. Similar thing here. We want to serialize this, so let's actually, we can just simplify this whole thing. So if someone passes an NVP in our stream operator, we simply serialize the name, call this serialized value that we'll create in a bit, and then we add the closing brace. Now, serialized value is going to be a private function. Serialize value. We want to be able to pass different things to it, so let's add a template argument, template type name t. We're not going to be changing our t, so we can just accept it by reference to const. And then I say by default, we just stream it. Something like that. But now, of course, we want to be able to define different behaviors for the different types of things we accept here. So the first thing we did before was remove this const expression if statement, where we have a special case for strings. Let's reintroduce that. I'll use a requires expression here, that's a C+20 feature, but you can also use Svine if you don't have C+20 available. We were using is convertible. If it's convertible from our t to a string, then we add some quotes. Isn't there even an SD quoted? There we go. That's even cleaner. Okay, what's next? The address one. Yes, let's add one for that. So I'll just add another specialization here. Now if we get past the class, then we're going to make the assumption that the user has defined a serialized function for this class. And I guess the user will need an instance of our writer class, so it can actually pass the members one by one to the writer. Then we're getting a call to serialized value is ambiguous. I see what's going on here. An std string is of course also a class, so it's going to match this serialized value, but it'll also match this serialized value. So let's make it unambiguous by making this required expression slightly more complete. We'll simply say, okay, use this specialization if you are a class, but you are not a string. Let me negate that. Okay, so now this all seems to get parsed correctly. All that's left is to define the serialized function. So this is what the user would do if they want to enable support for serializing addresses. And here, if you pass an address, that means that you first write the street name. And then we write the house number. Okay, and of course here serialize itself is already taking care of the complete serialization, so we don't need to actually stream this. That's better. If I now compile, we have a lot of tests failing. Well, that's to be expected. We made a lot of changes, but luckily these tests are warning us about the mistakes we're making. So let's start at the top. Even built-in types are no longer correctly serialized. Let's see what's going on here. It seems the built-in types are getting quoted. So why are they getting quoted? That means that the is convertible to is triggering here. That is surprising. No, this is what's going on. We simply still have the quotes here. These are of course no longer needed, because we've now said it's the responsibility of the serialized value function to correctly accept the value that's to be serialized and do this completely, including any quoting that might be needed. Let's try this again. Now we see only the last test is failing. Let's check what's going on here. Okay, so now we see that we're not correctly dealing with the case of getting multiple NVPs passed to us. That makes sense, we've never really dealt with that yet. So let's deal with that. But first let's write a separate test just for this, because this seems like a more basic elementary requirement. As a matter of fact, I'm also going to document this one. Serialization can handle multiple name value pairs. Now I'll just add an extra test case here. Multiple NVPs are serialized correctly. Let's see, what if we would just write these two NVPs? Then we would expect this to end up as a comma-separated set of NVPs. So after the first one, we'd have another hello, but now it's a true value. Let me actually just use a different name here. Goodbye. This looks like it's valid JSON. Now, if we run this, of course, this is going to fail because we haven't implemented anything new yet. And indeed it does. So let's first fix this. What we're now going to do is we're going to distinguish between the first NVP that's written and any further ones. We'll just add a simple Boolean. And then if something's being written and this is not the first MVP, then we first add a comma to separate it from the previous ones. And of course, we set first MVP to false at the end of this function. Now suddenly we get a lot more test failures, so clearly this hasn't really fixed anything. Let's see what's going on. The first one, NVP with built-in type is correctly serialized. That's already going wrong. So what we see here is that we're getting back comma hello colon true. This comma is because even though we reset our string stream over here, we never reset our writer. So the writer is still thinking it's now getting a second NVP. So let's just split this test up so we have a new writer for every different built-in type. We'll have one for the int case. One for the Boolean case, which of course has a separate writer. And last we will have one for the double case. Okay, so if I now look at the tests, we see that int, bool and double are all serialized correctly again. That brings us back to the multiple NVPs test. This one is still not passing, so apparently we still haven't fixed everything yet. It seems we're still outputting these unnecessary braces, so let's fix that as well. So now you can really see how this test-driven development is guiding us always towards the answer. You can make small changes, we see immediately whether they're correct or not, and if they're wrong, we know that the mistake is in the last few lines. So it's a very convenient way to do your software development. So if you don't have your first name value pair, so let's do it this way. If you have the first name value pair, then you get this opening parentheses. Okay, so now we still have this closing parentheses to deal with. It's now still going to be printed every time. If I just run the test now, our input for this one is now hello, goodbye. So we see that here the opening parenthesis is now gone because we are dealing with a second item, but we still have this closing parenthesis, which we don't really want. So what you actually want to do is only add this closing parenthesis when we're done writing out everything to our JSON file. But that means we need to know when we're done. And at the moment, we don't have any way to signal this to our writer yet. There's no way of, say, closing the stream or flushing everything. So let's follow the RAII approach. Resource acquisition is initialization. And simply say that whenever your writer is deconstructed, that's when we flush our stream and we assume that the document's ended. So I'll just add a deconstructor here. So just add a destructor here. You say, okay, whenever we write, that's when we actually close our document. That's now when we're done. And then we no longer output this one over here. Let's see if that works. Of course not, because we still have to update our test to handle this new behavior. So we want our writer to be deconstructed whenever we're done. So let's just add it in a local scope. That should be one test fixed. Yep. Then we do this for every test. Okay, int, bool and double are now all serializing correctly. Let's look at the multiple NVPs. Okay, so there's still one small mistake. It's actually not test reference. There's one space too many. Now if we rerun, we're still not there. There's one space at the end. We said that we want to have extra spaces. Now we see that multiple NVPs are all serialized correctly. Now there's the string one still. That should just be a matter of updating the way of working with our writer. We create a new writer and we destruct the writer whenever we're done with it. And I forgot to clear the stream. That should still happen, of course, because we are reusing the same stream. Okay, that's now also passing. Now we get back to where we ended up before. We're trying to serialize this address class. Again, I'll first update the test to deal with this RAII way of working. Okay, so now let's see what difference we still have. This looks very similar. Hello, street name, some street, house number. I'm not immediately seeing the difference. It seems we're missing an extra closing parenthesis. So now the interesting question is, what is this parenthesis? Actually, this should have a space. So we expect 2 parentheses, but we get only 1. So it seems like we're not correctly closing off the nested address class. So whenever we're serializing a class, this itself is an object and should be in braces. So let's actually add that. Now I see that there's an extra opening brace here. Where is that coming from? Ah, right, I understand now. This one is of course not needed because the contents of a class is a series of name-value pairs, and we're going to be opening up the brace with the first one already when writing out that first name-value pair. Okay, now we have all tests passing. However, my gut feeling is telling me that if we start working with some more complicated examples, we'll find that there's still some things going wrong with our commas and our braces when we nest different structs. So let's create some more complex test cases just to see if we can stress test our current implementation. Say we had a struct person, and the person has a name and an address. So now we're going to be nesting our custom classes. So let me just add a serialize function here. If we are passed a person, let's call it P. We first output the name of that person and then the address. In theory, this should be enough to now serialize our persons. So let's try that out with a test. So now we have a person Bob with an address. So we would expect this to be Bob, comma, the address, then of course an extra parentheses here. And I think we said we always added a space after every opening brace. Let's see if this works. It looks like it does not, so let's double check what the difference is between the output of our serialization system and the test. First I forgot the name here. Let's fix that. Name should be Bob, and then address should be this thing. That's the first mistake. That's one on the test side, not on the actual implementation side. Let's check again. Hello, name is Bob, address is, and then we have an object, or at least that's the idea, but it's not what we're seeing here. So my gut feeling that the braces would go wrong when we start nesting things is indeed correct, it seems. We need an extra opening brace here. So let's see if we can make that work. I think we need to rethink a bit how we deal with nesting of serialized calls and ensuring that all the braces are correct. Instead of having this ad hoc solution of adding an open brace only when you're at the first one, let's do it differently. Every time we call serialize on an object, on a C++ class or struct, let's add the braces there, so that even when we start recursing, we always have the brace around the object, and then we'll deal with the start document braces separately. And since we're already following an RAI way of working, let's just do it in the constructor. This gets a bit closer, but we're not there yet, because now we have this stray comma here. We said before that as long as we are not in the first NVP, we need to add this comma. But this of course no longer holds once we start nesting, because we should restart our count every time we get into a new object. So let's also fix that. Here we can simply reset our first NVP equals true. So every time we're going one level deeper, we again know that we need to add our commas. And now we see that all tests are passing. Great. We can even deal with nested structs. And that's it for this episode. We are now able to serialize custom classes and structs, even more complex ones that nest other classes and structs. According to our requirements, there's one big feature remaining: the ability to serialize list-like types, vectors, arrays, std lists. This will be the main objective for the next and last episode, and it's going to be a cool one because we'll be using a lot of C++ features to make a nice generic implementation. We'll be using concepts and requires expressions, as well as writing some type traits. So I hope you'll join me again in the next episode. As always, you can find the code on GitHub. There's a link down in the description. Thanks for watching. I'll see you next time.